silicon or epitaxial, third and fifth semiconductors. Most semiconductor solids exhibit a complex interplay between carrier confinement. Enhanced quantum dots coupling for higher mobility is often accompanied by the increase of intragap tail states that shrink the electronic gap of the quantum dot solid. Recently, encouraging progress has been achieved for quantum dot solids, showing balanced charge transport for both polarities that preserve discrete quantum confined electronic states. The Nobel Prize in Chemistry 2023. The Royal Swedish Academy of Sciences had decided to award the Nobel Prize in Chemistry 2023 to Mwangi G. Buendi, born in 1961 in Paris, France, get his PhD from University of Chicago, and from the and professor at Institute of Technology. The second one is the Louis E. Bros, born in 1943 in Cleveland, USA, got his PhD from 1969 from Columbia University and professor at Columbia University, New York. The third one that get the Nobel Prize in Chemistry 2023 is Alexei Yakimov. He is born in 1945 in the former USSR, got his PhD in 1974, and live in New York, USA. Mongi G. Bondi, Louis E. Bros, and Alexei Yakimov are awarded the Nobel Prize in Chemistry 2023 for the discovery and development of quantum dots. These tiny particles have unique properties and now spread their light from television screens and LED lamps. They catalyze chemical reactions and their clear light can illuminate tumor tissue for a surgeon. These scientists added color to nanotechnology. These illustrations show that quantum dots in different colors. Quantum dots given us new opportunities for creating colored light. Size matters on the nanoscale. In the nano world, things really do behave differently. Once the size of matter start to be measured in millions of a millimeter, strange phenomena start to occur. Quantum effects that challenge our intuition. The 2023 Nobel Prize winners in chemistry have all been pioneers in the exploration of the nanoworld. In the early 90s, Lewis Bros Alexei Yakimov succeeded in creating independently of each other quantum dots, which are nanoparticles so tiny that quantum effects determine their characteristics. In 1993, Mongi Buendi revolutionized the methods for manufacturing quantum dots, making their quality extremely high, a vital for their use in today's technologies. Thanks to the work of these scientists, humanity is now able to utilize some of the peculiar properties of the nanoworlds. Quantum dots are now found in commercial products and used across many scientific disciplines from physics and chemistry to medicine, but we are getting ahead of ourselves. Let's uncover the background to the Nobel Prize in Chemistry 2023. For decades, quantum phenomena in the nanoworld were just a prediction. When Alexei Yakimov and Louis Bros produced the first quantum dot, scientists already know that they could, in theory, have unusual characteristics. In 1973, a physicist had already predicted that the nanoparticles would not behave like other particles. He explored the theoretical consequences of the famous Schrödinger equation, which shows that when particles which show that they become extremely small, there is less space for the material's electrons. In turn, the electrons, which are both waves and particles, are squeezed together. Froelich realized that this would result in drastic changes to the material's properties. Researchers were fascinated by this insight and using a mathematical tools, they succeeded in predicting numerous size-dependent quantum effects. They also worked to try to demonstrate them in reality, but this was easier said that done because they needed to sculpt a structure that was about a million times smaller than a pinhead. Few people thought quantum effects could be utilized. Still, in the 1970s, researchers succeed in making such a nanostructure. Using a type of molecular beam, they created a nano-thin layer of coating material on top of a bulk material. Once the assembly was complete, they were able to show that the coating's optical properties varied depending on how thin it was, an observation that matched the predictions of quantum mechanics. This was a major breakthrough, but the experiment required very advanced technology. Researchers needed both an ultra high vacuum and temperatures close to absolute zero, so few people expected that quantum mechanical phenomena would be put to practical use. However, now and again, science offers up the unexpected, and this time the turning point was due to study of an ancient invention, colored glass. A single substance can give glass different colors. The oldest archaeological finds of colored glass are from several thousand years ago. Glassmakers have tested their way to an understanding of how glass can be produced in all the colors of rainbow. They added substances such as silver, gold, and cadmium, and then played with different temperatures to produce beautiful shades of glass. In the 19th and 20th centuries, when the physicists started to investigate the optical properties of the light, the glassmakers' knowledge was put to use. Physicists could use colored glass to filter out selected wavelength of lights. To optimize their experiments, they started to produce glass themselves, which led to important insights. One thing they learned was that a single substance could result in completely different colored glass. For example, a mixture of cadmium selenide and cadmium sulfide would make glass turn either yellow or red. Which one it became depended on how much the molten glass was heated and how it was cooled. Eventually, they were also able to show that the colors came from particles forming inside the glass and that the color depended on the particle size. This was more or less the state of the knowledge at the end of the 1970s, which when one of this year's laureates, Alexei Yakimov, a recent doctoral graduate, started working at the institute in what was when the Soviet Union. Alexei Yakimov maps the mysteries of colored glass. The fact that a single substance could result in different colored glass interested Alexei Yakimov because it is actually illogical. If you point a picture in cadmium red, it will always be cadmium red unless you mix in other pigments. So, how could a single substance give glass of different colors? During his doctoral degree, Yakimov studied semiconductors, important components in microelectronics. In this field, optical methods are used as diagnostic tools for assessing the quality of semiconducting materials. Researchers shine light on the material and measure the absorbance. This reveals what substance the material is made from and how well ordered the crystal structure is. Yakimov was familiar with these methods, so he began using them to examine colored glass. After some initial experiments, he decided to systematically produce glass that was tinted with copper chloride. He heated the molten glass to a range of temperature between 500 and 700 degrees Celsius, varying the heating time from 1 hour to 96 hours. Once the glass had cooled and hardened, he X-rayed it. The scattered rays showed that the tiny crystals of copper chloride had formed inside the glass, and the manufacturing process affected the size of these particles. In some of the glass samples, they were only about 2 nanometers, in others, they were up to 30 nanometers. Interestingly, it turned out that the glass light absorption was affected by the size of the particles. The biggest particles absorbed light in the same way that copper chloride normally does, but smaller the particle, the bluer the light that they absorbed. As a physicist, Yakimov was well acquainted with the laws of quantum mechanics, and quickly realized that he had observed a size dependent quantum dot. Quantum effects rise when particles shrink. This illustration shows quantum effects arise when the particles shrink. This was the first time someone had succeeded in deliberately producing quantum dots, nanoparticles that cause size dependent quantum effects. In 1981, Yakimov published his discovery in a Soviet scientific journal, but this was difficult for researchers on the other side of the Iron Curtain to access. Therefore, this year's next Nobel Prize laureate in chemistry, Louis Brass, was unaware of Alexei Yakimov's discovery when, in 1938, in 1983, he was the first researcher in the world to discover size-dependent quantum effects in particles floating freely in a solution. Brass shows that the strange properties of particles are quantum effects. Louis Brass was working at Bell Laboratories in the US with the long-term aim of making chemical reactions happen using solar energy. To achieve this, he was using particles of cadmium sulfide, which can capture light and then utilize its energy to drive reactions. The particles were in a solution, and Brass made them very small because this gave him a larger area on which the chemical reactions could take place. The more a material is chopped up, the greater the surface area it will expose to its surroundings. During his work with these tiny particles, Bruce noticed something strange. Their optical properties changed after he had left them on a lab bench for a while. He guessed that this could be because the particles had grown, so to confirm his suspicions, he produced cadmium sulfide particles that were just about 4.5 nanometers in diameter. Bose then compared the optical properties of these newly made particles with those of the larger particles, which had a diameter of about 12.5 nanometers. The larger particles absorb light at the same wavelength as the cadmium sulfide generally does, but the smaller particles had an absorption that shifted towards blue. Just like Yakimov, Bruce understood that he had observed a size dependent quantum effect. He published his discovery in 1983 and then started investigating particles made from a range of other substances. The pattern was the same: the smaller the particle, the bluer the light they absorbed. The periodic table gained a third dimension. This is where you may be tempted to ask, why does it matter if a substance's absorbance is slightly more towards blue? Why is that so amazing? Well, the optical changes revealed that the substance characteristics had completely changed. A substance's optical properties are governed by its electrons. The same electrons also govern the substance's other properties, such as its ability to catalyze chemical reactions or to conduct electricity. So, when researchers detected the changed absorption, they understood that they were looking at an entirely new material. If you want to understand the magnitude of this discovery, you can imagine that the periodic table suddenly gained a third dimension. An element's properties are not only affected by the number of electron shells and how many electrons there are it in the outer shell, but at the nano level, size also matters. A chemist who wanted to develop a new material had another factor to play with. Of course, this tickled researchers' imaginations. There was just one problem: the methods Bruce had used to fabricate nanoparticles generally result in unpredictable quality. Quantum dots are tiny crystals, and the ones that could be produced at the time often contained defects. They were also of varying size. It was possible to control how the crystals were formed, so the particle overage had given an average size, but if researchers wanted all the particles in a solution to be about the same size, they had to sort them after they were made. This was a difficult process that hindered development. Wonky Bondi revolutionized the production of quantum dots. This was a problem that this year's third Nobel Prize laureate in chemistry decided to solve. Mongi Buendi started his postdoctoral training at Louis Brass Laboratory in 1988, where intensive work was underway to improve the method used to produce quantum dots. Using a range of solvents, temperatures, and techniques, they experimented with a variety of substances to try and form well organized nanocrystals. And the crystals were getting better but were still not good enough. However, Boandi didn't give up. When he started working as a research leader at MIT, he continued his efforts to produce higher quality nanoparticles. The major breakthrough came in 1993 when the research group injected the substances that would form nanocrystals into a heated and carefully chosen solvent. They injected as much of the substances as was necessary to precisely saturate the solution, which led to tiny crystal embryos beginning to form simultaneously. Then, by dynamically varying the temperature of the solution, Mongi Bondi and his research group succeeded in growing nanocrystals of a specific size. During this phase, the solvent helped give the crystals a smooth and even surface. The nanocrystals that Bondi produced were almost perfect, giving rise to distinct quantum effects. Because the production method was easy to use, it was revolutionary. More and more chemists started working with nanotechnology and began to investigate the unique properties of quantum dots. The luminous properties of quantum dots find commercial uses. 30 years later, quantum dots are now an important part of nanotechnology's toolbox and are found in commercial products. Researchers have primarily utilized quantum dots to create colored light. If quantum dots are illuminated with blue light, they absorb the light and emit a different color. Modifying the size of the particles makes it possible to determine exactly what color they should glow. The luminous properties of quantum dots are utilized in computer and television screens based on QLED technology, where the Q stands for quantum dot. In these screens, blue light is generated using the energy efficient diodes that were recognized with the Nobel Prize in Physics 2014. Quantum dots are used to change the color of some of blue light, transforming it into red or green. This makes it possible to produce the three primary colors of light needed in a television screen. Primarily, quantum dots are used in some LED lamps to adjust the cold light of the diodes. The light can then become as energizing as daylight or as calming as the warm glow from a dimmed bulb. The light from quantum dots can also be used in biochemistry and medicine. Biochemists attach quantum dots to biomolecules to map cells and organs. Doctors have begun investigating the potential use of quantum dots to track tumor tissue in the body. Quantum dots are thus bringing the greatest benefit to humankind, and we have just begun to explore their potential. Researchers believe that in the future, quantum dots can contribute to flexible electronics, sensors, slimmer solar cells, and perhaps encrypted quantum communication. One thing is certain that there is a lot left to learn about amazing quantum phenomena. So, if there is a 12-year-old Dorothy out there looking for adventure, the nano world has a great deal to offer. And then the last, there is a references from different articles from where the material I got. Thank you so much.